Hello everyone, we're discussing nuclei. And we have already seen properties of nuclear force. Now, let's talk about binding energy. Look here. This is a nucleus, and in this nucleus, n number of protons are present, and let's say m number of, or let's choose n1 and n2. N1 protons are present and N2 neutrons are present, and mass of the nucleus is m. What is m? Mass of the nucleus. N1 number of protons, N2 number of neutrons. Mass of proton, we'll call it MP. Mass of neutron is Mn. So one would expect that this M should be N1 protons, each of mass MP, plus N2 neutrons, each of mass Mn. That's what you would expect. If I've got N1 number of protons, N2 number of neutrons, multiply N1 with Mp, that gives you total mass of protons. N2 multiplied by Mn, this gives you total mass of neutrons. But what is observed that this relation is not correct. M is not this much. What is observed that M is in fact less than N1 MP plus N2 Mn. That's what is observed. Total mass of the nucleus is less than the total mass of all the nucleons, all the components of the nucleus. If you take their total mass, then this is what is the correct observation. So how do you explain something like this? Now let's understand this part over here. These are all the nucleons, protons and neutrons. And let's say at the beginning of universe, we are trying to create a nucleus which has these many protons and these many neutrons. And let's talk about the very beginning. So the very beginning, all these nucleons, protons and neutrons, they are well separated. These well separated nucleons then do what? Then they move towards each other. That's what I explained in the previous lecture. So these nucleons, they are moving towards each other, and when they are in the range of nuclear force, the range where nuclear force becomes effective, these then simply come together and form a big nucleus. And in the process, what happened? Let's talk about two protons. It will be easier to visualize the whole concept then. These are the two protons, positive charge. They are repelling each other with Coulomb's repulsion. And then, let's say they were moving like this towards each other. Because of Coulomb repulsion, their velocity is decreasing. And just when they arrive at the boundary of the nucleus which they are going to form, the range where nuclear force becomes effective, right at that moment, their velocity becomes what? Zero. Now, this nuclear force is very strong force. It does what? It then attracts these nucleons, these protons, and because of that, these protons gain what? Some kinetic energy. But eventually, when everything settles down, this kinetic energy is not present. So, the energy part is coming out. This energy which comes out, Einstein says, has some mass. Now, some mass has gone out, and therefore total mass of all the nucleons taken together will never give you mass of the nucleus which these nucleons are going to form. So, let's say when they are well separated, total mass is m dash. We'll write statements for m dash, m and all these things, just don't worry. What is m dash? When all these nucleons are well separated. So this m dash is nothing but n1 multiplied by mp plus n2 multiplied by mn. This is m dash when they are well separated. Delta m, we are interested in the mass which is gone because of that loss of kinetic energy. This delta m is m dash minus m. This m which is mass of the nucleus, m dash is this much. This delta m which is m dash minus m, energy corresponding to this delta m is what? The energy part which according to Einstein this delta m has is delta m into c square. This delta m c square, delta m which is m dash minus m, is called binding energy of the nucleus. If you provide this much energy back to this nucleus, then all the nucleons will move away from each other. This nucleus will disintegrate and you get what? All these nucleons when they have very large separation. In the reverse or the original direction was what? They all came together, released kinetic energy. That kinetic energy is nothing but binding energy, and this binding energy has certain mass which is delta m. That delta m tells us that observed mass of the nucleus will be always less than the total mass of all components, all the constituents, all the nucleons taken together. Note down this much, and if you have understood the concept, we'll write a few statements. If you have understood the concept, the basic thing, how come m is less than this? If you are comfortable with all this, then write down yes in the comment box. Write down the statement. M is mass of the nucleus. M is mass of the nucleus. M dash is mass of total mass of all the nucleons, total mass of all the nucleons when they are well separated, that is, they do not interact with each other. That is, they do not interact with each other. Infinite separation. Delta M is called mass defect. Delta M is called mass defect. Energy equivalent of delta M. Energy equivalent of delta M is delta M C square is delta M C square, which is called binding energy of the nucleus. Which is called binding energy of the nucleus. Write down the whole concept also just for your understanding. It is observed that M is always less than M dash. It is observed that M is always less than M dash and because of this we can say that some energy is released into the universe at the time of formation of the nucleus. At the time of formation of the nucleus. This energy is nothing but binding energy. Similarly, if we can provide energy equal to binding energy to a given nucleus, then it will disintegrate into constituent nucleons. it will disintegrate into the constituent nucleons. Now we can also write N1 as Z and N2 as A minus Z. Elementary thing. For simplicity, I have used N1 and N2. You can put value of N1 as what? Z. And number of protons will be what? A minus Z. Now, when we talk about stability of a nucleus, how stable it is, how easy it is to break it apart into the components, all those protons and nucleons, then instead of dealing with binding energy, we deal with binding energy per nucleons. That is binding energy divided by A. What is this? We'll understand the concept with the help of some numerical values. It will be easier for you to grasp the concept then. Put down this much fast and then I'll erase it and we'll understand the concept of binding energy per nucleon. What is it and how effective it is for the stability of a nucleus. Put down everything fast. Suppose there are two elements A and B. Binding energy of A is 20. Binding energy of B is 10. The mass number of A is 5. Total number of nucleons is 5 for A, and mass number for B is 2. Total number of nucleons. Element A has 5 nucleons, 5 protons and neutrons all together inside the nucleus. B has 2 nucleons, proton and neutron inside the nucleus. This is the binding energy of A, this is the binding energy of B. So, normally what would you find that? What would you expect that? This thing should be more stable. And why would you do that? Because if you take the nucleus of A, then if you give it 20, let's say joules, just for your understanding, if the nucleus of A is given 20 joules of energy, then all the protons and neutrons, they can be separated and can reach infinity. Whereas nucleus of B, if you give it only 10 joules, then you can separate the nucleons and it's easier to give 10 as compared to 20. So the perception is that This is more stable. It needs more energy. It needs less energy. You can easily defragment this thing with 10 joules of energy. But let's introduce binding energy per nucleons, total number of nucleons. So binding energy per nucleon for A is 20 divided by 5, which is coming 4. Binding energy per nucleon for element B is coming 10 by 2, that is 5. Now let's talk about 4 and 5 per nucleon. So just understand this way. As I told you in the previous lecture, every nucleon, it doesn't interact with all other nucleons. There is a particular range in which nuclear force is effective. So this nucleon or this proton or neutron is going to interact with all others which are present, let's say, in this range. This is the size of the nucleus, imagine this way. But this neutron is going to interact with all those which are present in this boundary. A nucleon over here will interact with those which are present in this boundary. That's how we say that density is everywhere what? Same. So when you provide element A, if you provide this element A with 20 joules of energy, then we say that interaction of a particular nucleon with other nucleons can be, that interaction, it can be minimized or the interaction can be removed provided you provide 4 joules of energy. Whereas for B, if you want to get rid of this interaction between the nucleons, then you need 5 joules energy per nucleon. Now, if I give a material, if you have a material, now talk about not a nucleus but collection of nucleus. Forget about the electron cloud for the time being. Let's say this is the nucleus of A, another nucleus of A, another nucleus of A, another nucleus of A, collection of nucleus of A. Now just assume that you have a solid throughout for the understanding. Yes. Imagine there are no electron clouds and you have got a very dense material made up of A. So this dense material, it requires what? To break it apart, to get rid of the interaction between the nucleons, it demands only what? 4 joules per nucleon. Whereas a similar material or a different material, which is B, again the same type of dense thing where all the nuclides of B type are present, remove the electrons. Now this material demands what? If you give it 5 joules per nucleon, then you can extract 1 nucleon out. So if you can extract 1 nucleon out by giving how much energy? 5. And in this case, you can extract the nucleon by giving it only 4. That means what? This thing is less stable as compared to this. Whenever we provide energy, that energy will be distributed in the whole sample. Understand again. So you start with 1000 joules of energy. You're not starting with 20, or you're not starting with 10, you started with 1000 joules of energy. The moment you give this 1000 joules of energy, this energy is going to spread out for every nucleon present inside the nucleus. So every nucleon gets this 1000 joule energy, not 1000, 1000 divided by the number. So as you provide the energy, everyone receives that. For A, the moment you get 4, that nucleon will come out. That means we have simply disintegrated nucleus of A. Whereas for B, the moment you start releasing energy, it spreads out uniformly. Demand is what? The moment it becomes 5, the moment you get 5 per nucleon, everything, all the nucleons will start coming out from the inside. That means a complete defragmentation takes place, which tells us that energy requirement or binding energy of 20 and 10, it is not a true criteria for the stability. Instead, binding energy per nucleon will give us stability of the nucleus. Look at the data which I have given you. 20 is greater than 10, but 4 is less than 5. So once you go for stability part, we always look for binding energy per nucleons. I'll try to explain this thing again so that you feel comfortable, but let's write down the statement first. Stability of a nucleus is not decided by its binding energy. Stability of a nucleus is not decided by its binding energy, but is decided by binding energy per nucleons. Binding energy per nucleons. In the given example, although binding energy of A is greater than that of B, it is less stable. Because binding energy per nucleon for A is less than that for B, Let me explain the per nucleon part again so that you feel comfortable. Look here. This is collection of A's. This is collection of B's. Element A, element B. Now we are giving the whole setup of A is being given some energy, and similarly you provide energy to the sample B. Now once you supply the energy, this energy will distribute itself over all the nucleons. Similarly, when you supply the energy will be received by all the nucleons. That means everyone will get its share. So, if I start giving energy and gradually energy is increasing, the moment per nucleon energy for A becomes 5, for A it is 4. The energy per nucleon, the distribution per nucleon becomes 4. They start kind of coming out of this whole packet. The moment energy per nucleon of B becomes 5, disintegration of B starts. Let's start from this. I hope you understand the setup. Collection of A's, collection of B's. And we have started kind of heating this sample and kind of heating this sample. So when you are supplying the heat, that heat distribution takes place, every nucleon gets its share, and you are providing energy at constant rate. Both these samples, they are receiving energy at the same rate. You have two similar sources. The moment distribution is such that it becomes 4, its disintegration starts. The moment every nucleon gets 5, its disintegration starts. And if I ask you which one should be more stable, then you will say what? To reach 5, it will take longer as compared to what? 4. They will receive 4 first, then they will receive what? 5. Which means, which is more stable? A is more stable than B. My fault. Which is more stable? B is more stable than A, because the A's, they get 4 first, and then B's, they get what? 5. So which one gets the minimum criteria for disintegration, which reaches that stage first? A. And therefore its disintegration starts first. You keep supplying the energy level increases, and when it becomes 5, now disintegration of B's starts. That means it took longer. That means it is much more stable. Are you comfortable with this concept now? Tell me fast, yes or no? One more try. Just imagine there are 2 classrooms, and there is no way you can count number of students in the classroom. So in these 2 classrooms, you see that a big crowd is present. You cannot count it. You can see that many students are present. Now, this is classroom A. This is classroom B. Now, those present in classroom A, they demand that all those who are present in the classroom A, they demand that if you give them 4 rupees, each, then they will come out of the classroom. Just imagine this way. Whereas those in B, They demand that if they each are given 5 rupees, then only they will come out of the classroom. What you are looking at, you're looking at a big crowd, and you have been told that everyone demands 4 rupees. You see again a big crowd in classroom B, and you have been told that everyone should be given 5, then only they will empty the classroom. I think it's easier for you to understand which one is more stable. This, they need what? 5 rupees. If you give them 4 each, the person who is coming, he gets an idea that this classroom, it's easier to disintegrate. Everybody will get 4 and they will go away. This classroom, it's a bit difficult because everybody should get 5, then only they will come out. That means this classroom is more stable. Now, when graph of binding energy per nucleons versus mass number A or total number of nucleons is plotted, it looks like this. This is the shape of binding energy per nucleon. This shape tells us what? This is A. This is B. This is 2, total number of nucleons. This is 4, a different example. Not the previous one, a different example. This is C. This is D. Total number of nucleons 50, total number of nucleons 100. Total number of nucleons for A 2, for B 4, for C 50, for D 100. Binding energy per nucleon, let's say is 10, is 15. Over here, let's say this is 30. I'm taking values randomly, but according to the graph. This one is 20. These are the values for binding energy per nucleon. The graph is rising and then is coming down. Look at the shape. It rises first and then is coming down. The horizontal axis is giving you total number of nucleons present inside the nucleus, and the vertical axis gives you binding energy per nucleon. Now, look at the numbers. Mass number 2, double of that is 4, 50, double of that is 100. Well, I've already told you that which one is more stable. Or let me ask you first, between A and B, which is more stable? Write down fast in the comment box. Between A and B, which one is more stable for the pair of A and B? Write down between C and D, which is more stable. Between C and D, which one is more stable? So I hope everybody will try to answer correctly. What is binding energy per nucleon? 10. Binding energy per nucleon? 15. Binding energy per nucleon, it gives you what? Stability. The greater the binding energy per nucleon, more stable your nucleus is. So B is more stable than A. B is more stable than A. This is for stability. More stable. Now, between C and D, C, its binding energy per nucleon is 30. D, its binding energy per nucleon is what? 20. More binding energy per nucleon. This is that classroom where everybody demands 30 rupees should be given. This is that classroom where only 20 rupees is the requirement. And therefore, you can easily disintegrate this one. That means 30 is more stable. C is more stable than D. Which means what? If B is more stable and out here C is more stable, then the stability part is giving us a way of creating energy. What is that way? If I can do this, A plus A, and then I get B. If I can combine two nucleus of A, 2 plus 2 will give us what? 4. Then from less stable I reach a more stable stage. And everybody knows when you become more stable, to do that you have to release energy out of you. If I group two A's, I get B and I become more stable. To become more stable, you have to release energy. This energy, when comes out, is called fusion. Look here. If we can break this D into two nuclides of 50 and 50, then it becomes what? C. As it becomes C, stability increases. If stability increases, that means energy should be coming out. So when you break D into C and C, you are increasing the stability, energy is coming out. This energy is fission energy. Fission, atomic bomb. Fusion, thermonuclear bomb. Now what is happening here? How much time I've got? I will take 2-3 minutes more, just so that these things are clear, and then next class we'll take some more examples, but just stay for 2-3 minutes more. When I say that A and A, they group together, what happens? Look here. A, binding energy per nucleon is 2. Binding energy per nucleon is 10. How many nucleons are present? 2. So what is the energy of A? 20. What is the energy of A? 20. What is energy of B? Energy of B is what? 4 multiplied by 15, which is what? 60. But look at this. This equation is not balanced. 20 plus 20 over here 60. Equation is not balanced. To balance this thing, I need to add another 20. This 20 is fission energy. Now, let me give you the reasoning behind this 20 coming out in the form of fission energy. What is 2 total number of nucleons? What is 10 binding energy per nucleon? Which is what? Giving us total binding energy of 20. Now understand this 20. At the time of Big Bang, when universe was forming, you had 2 well separated nucleons. Understand this. You had 2 well separated nucleons. They come and form a nucleus, which is A, and in the process 20 joules comes out. That's what I've already told you. 2 nucleons, they come, form a nucleus, in the process mass defect takes place, energy comes out, which is 20. Take another A, again when it forms, 20 comes out. So the universe has got how much energy? 20 and 20 when it formed A. Now imagine B. Take the case of B. How many nucleons are 4? How many nucleons are present in B? 4. All the 4 nucleons are well separated. They come together, form a nucleus, that is called B, and in the process energy comes out. That energy is what? 60. So the universe has got how much energy? 60. When B forms, universe should get 60 joules. But now you decided that you will fuse A with another A and A. So when you are trying to fuse A and A, you are getting what? B. But so far, universe has got 20. Universe has got 20. But if you fuse A and A together, you get D. Universe demands that it should get 60. So how do you get 60? How do you give the universe 60? This A and A fusion process releases another 20 joules, thus making total energy count 60. This 20 joule once comes out gives you a more stable nucleus. Again, let me explain the thing with a easier setup. I'll talk about fission in the next class, the fusion part. Try to understand this example. Suppose there are 2 theaters, and these 2 theaters are what? A and B. Or you can say 3 theaters, A and B. There are 3 theaters, A and B. In A, when 2 nucleons go, they have to shell out 10 rupees. This is the ticket cost. Watching the movie, you have to pay 10 rupees per person. So, the moment these 2 nucleons, they go and sit in the first theater A, the person at the counter, he gets how much money? 2 multiplied by 10, 20. So these 2 are sitting inside the first theater. Similarly, another 2, they go to the same type of theater A, where a ticket cost is what? 10 rupees per person. So how much money the person at the counter gets? Another 20 rupees. But now once inside they found that it was a horror movie. Just imagine. It was a horror movie and the big theater only two are sitting. In another big theater only two are sitting and they're watching a horror movie. So they come out and they say that it's a horror movie type of thing. It would be better if you group us four together and make us sit in a single one. The person at the counter says, okay, I can do that. But if you four sit together, ticket count is now 50 rupees per person. So you say what? Okay, we'll do that. 15 into 4 is what? 60. You have already given 20 to the person outside. You already given 20 to the person inside. Now he says that total money requirement is of 60. Extra which should come out from you is what? 20. The person who is collecting the money at the ticket counter is universe. And this is first nucleus. This is type first nucleus. And this is your second type nucleus B. Something similar happens with the fission part. I'll explain this fission process in the next class. If you have understood why this in red, the energy of 20 joule in red is coming out, then write down yes in the comment box and then you can leave. Thank you very much.